In this instructional video, we're going to review our answers to our homework assignment number 1 from Chapter 14, Kinetics. Now, on your assignment sheet from your note pack, you see that you had the following assignments of problems assigned in assignment number 1. These were problems coming from the back of Chapter 14, starting on page 618. So 11, 13, 15, 17, and 19, starting on page 618. Then you notice down here the assignment criteria for credit, and I said on your own paper, writing out the question completely, working your answer underneath to the correct solution. But friends, what I wanted to do was save you a little bit of time, and so what I've done for you is provided in some of those handouts from the previous day that already typed out. So number 11, I already typed it out. So I opened my book and wrote out the problem for you. Number 13, I wrote it out for you. So it's saving you the steps of all of this criteria for credit. And so what we'll do, instead of taking out our own paper, we're going to work these problems directly on this assignment sheet handout. And this can come in for your homework credit next time we see each other in class. So let's just check our work. It asks us, what is meant by the term reaction rate? Well, I'll share with you what I wrote, and you can find this directly in your note pack. The term reaction rate, we said, was the change in the amount of products or reactants over a given amount of time. Another way of saying the same thing is it's the speed of a reaction. What is the rate at which reactants disappear or the rate at which products appear? Your next question, we're checking concentration of reactants, surface area of reactants, temperature, and a catalyst were all possible correct answers for factors that affect reaction rate. We increase the speed of a reaction by increasing the concentration. We increase the reaction rate by increasing surface area. And the reaction rate also increases by warming the temperature. And the presence of a catalyst will speed up the rate of a chemical reaction. In the last part of your chapter, question 11, what information is necessary to relate the rate of disappearance of reactants to the rate of appearance of products? And know that this was called a rate expression. We need to know the stoichiometry of the reaction. This is where we take the change in concentration over the change in time. We place the stoichiometry, those coefficients, as a fraction, putting a negative sign for the reactants and a positive sign for products. And we'll be writing some of those, and I'll bring up the term rate expression that will come up in just a next question or so. Let's go on and talk about number 13. Consider the following hypothetical aqueous reaction. I think I'm going to go to a blank paper and tell me it's on. A goes to B. The flask is charged with 0.065 moles of reactant A in a volume of 100 milliliters. The following data were collected. So at time 0, that's the initial amount of reactant A, and you can see as time goes by, reactants get used. Moles of B will be asked for, followed by molarity of B. And that's why I highlighted 100 mLs, because I know when I take moles per liter, I come up with molarity. That might be a good little side note there, moles per liter. Now what we're being asked to do in this first highlighted bullet is to calculate the moles of B at each time in the table, assuming there are no moles of molecules of B at time 0, which makes sense. The reaction hasn't yet to start, so if I only have reactants, I have 0 moles of B. There are none produced, so at the very start I only have reactant and no product made. Then time goes by. Now remember, the same amount of reactant that gets consumed matches the product made. This is a 1-to-1 stoichiometric ratio. So the same number of reactant A, the moles that get used, is the same number of moles that form, just a 1-to-1 ratio. And so when I look at the interval between time 10 minutes and time 0, I started with an initial amount of 0.065 moles of A. And to arrive 10 minutes later, I now have remaining 0.051 moles. And so the difference of 0.014 would be how much of the moles of the product I made. So I'm just going to simply put that in, 0.014 moles of B. 20 minutes go by. Now keep in mind, I have to go back to the original amount every time I'm going to solve for how many moles of B form. So the interval here is now 20 minutes go by. I started with 0.65 moles. What's left of reactant A is 0.42 moles. So how much B formed would be 0.023. Go back to the zero amount every time. So now 30 minutes go by. How much of A was consumed? 0.065 minus 0.036. And how much of B then formed? Be 0.029 moles. And in the last interval, 40 minutes went by. So its time interval starting with 0.65 and the remainder of the reactant 0.31, and that's 0.034 moles of B were forming. So here reactants got used and products were made. Those numbers are in a sequential order that makes sense. Mole of A should decrease as product B increases. The last line here just simply asks us to change these moles of B into molarity of B. And so what I'll simply do there is just take moles and divide it by 0.1 liter, and I'll just fill in this last line as well. Of course, we have no molarity at time 0. 0.014 divided by 0.1 just slides the decimal, and I'll just fill that in for the remainder. So the number of moles divided by liters just switches the decimal one spot. Molarity is moles per liter, so we simply take moles divided by 0.1 liter and we arrive at that last grid. So we've done this. We've calculated the moles. Now a next question says, between time 10 minutes and 30 minutes, what is the average rate of the appearance of B in molarity per second? Well, okay, so now all of a sudden I have a unit here, molarity per second, but I have minutes in here. So let's just take a quick moment and change the minutes. 10 times 60 seconds would be 600 seconds is equivalent to 10 minutes. And then 30 times 60 would give us 1800 for the number of seconds in 30 minutes. And I'm just doing that because it simply asked me to do this in a molarity per second, but my timetable here was per minute. Alrighty. So this one, just keep in mind, this was shown in data table. But keep in mind the real trick here is to always subtract from the initial amount. And I'm going to write that just so that when you go back to study you'll remember that hint. Always subtract from the initial amount. That's just a good piece of advice. We'll add that on. All right, so now let's go back to this one. We're concentrating on the rate of appearance. So between time interval 30 and 10, how much of B appeared in a molarity per second unit? So the change in concentration of B over the change in time is what we're asked to solve for, an average rate. Well, at time 30, we had 0.029 molar. Whoops, I'm sorry, I got to get rid of that decimal. 0.29, I'll start that neater. 0.29 molar units. And at time 10, we had 0.14 molar units. So there's the delta concentration change. And the delta T would be 1800 seconds minus 600 seconds. So change in concentration over change in time, and we'll come up with a rate over a time interval. 0.29 minus 0.14 equal, divided by 1800 minus 600, and we found 1.25 e negative 4. And the unit there is molarity per second. So how quickly the product is appearing over the time interval of 10 minutes to 30 minutes, but calculated in a molarity per second unit. 15 asks us to calculate an average rate of reaction. So here we're given some time in seconds and the concentration of a reactant, acetonitrile. The following data were obtained. Notice we're being asked to calculate an average rate. So that's the change, let me move that up, the change in concentration of our CH3NC, this is methyl isonitrile, over its change in time. So that's what we're going to calculate. You know, in the last instructional video where I practiced with you calculating average rates, I wrote down all the work and I said eventually we'll let that go and just make that calculator work. Well, that's what I'm going to show you here, and just take as many notes as you need to make sense of how I'm solving it. Now keep in mind, we cannot have an average rate at an initial time 0. There's nothing to compare it to, so I'll just cross off that first line. And so when I compare line 2 to line 1, the change in concentration, 0.0110 minus 0.0165, divided by the time interval of 2000 minus 0. Even though my rate is negative, I do not report rates as negative. The negative is there to let me know the reactant is disappearing. Its amount value is decreasing, but rates are always reported as positive numbers. Let's keep going. 0.00591 minus the previous line, 0.0110, equal, divided by the time interval of 5,000 minus 2,000. And we get a rate reported as 1.696. Let's call that 1.7 times 10 to the negative 6. And that would be in molarity per second. Let me write that up on the top of this grid, and that will carry that unit all the way down. Keep going. 0.00314 minus 0.00591 equal, divided by the time interval of 8,000 minus 5,000. And its average rate is now coming out to be 9.23 times 10 to the negative 7th molarity per second. The next line, 0.00137 minus 0.00314, divided by 12,000 minus 8,000. How about 4.43 times 10 to the negative 7th? Is that a calculator match? And one more will fill out our chart. 0.00074 minus 0.00137 divided by the time interval of 15,000 minus 12,000. And that interval, 2.1 times 10 to the negative 7th. Every unit here is a molarity per second. So calculating an average rate over a time interval, we go to the previous line. We just compare one interval to the next interval. Ready? What's next? Graph that data versus concentration in an instantaneous rate. So an instantaneous rate versus what's called an average rate. The average rate we calculate by the change in concentration over a time interval. When we're asked to solve for an instantaneous rate, what should go off in your head is my test-taking tool page, how to calculate an instantaneous rate. We had practice with one of these in a previous lesson. Let's practice again. The first thing we need to do is enter these lists into our calculator. And the lists appear down here in the problem 14.15. So let's pull up our lists. And if I have something in the list, I'm going to just clear them out. All right, so my two lists are indeed empty. Time goes into the list 1, and concentration goes into list 2. So let's type them in. 0, 2,000, 5,000, 8,000, 12,000, and 15,000. List 1. List 2, 0.0165, 0.0110, 0.00591, 0.00314, 0.00137, 0.00074. And we have a match. Yes, I always like to make sure I typed in the same numbers, the same number of numbers in the two lists. All right, so we have those entered. We now want to know the exponential regression. So remember our test-taking tool, step 2. What we want to do is find the equation of exponential regression for these two lines. So here they are in my list. Remember how to do this? We hit Stat, Calc, and all the way down to choice 0, exponential regression. We want to do that for list 1, list 2, and hit Enter. So there's our equation, a very good correlation coefficient. We want to get that into our y equals. So I'm going to hit y equals, and if something is there, clear it out. To bring that equation over, the steps are to hit your vars, V-A-R-S. Number 5, statistics, your equation, and hit Enter. And now it's transferred that over for us, saved us all that typing. Now we're ready to find a first derivative, but here's a good recommendation. Take a moment and make sure your window is large enough. So hitting window, we have a graph that goes from 0 to 15,000. So it looks like my X max is not large enough. So I'm going to make it 20,000, something that will ensure that I have a large enough window. For y, we're kind of between the numbers 0 and 1, so that actually looks fine. So that I'll just leave alone. But I do want to check that so I don't get a domain error when I go to do my graphing. All right, so we have our equation in there. We've checked our windows. Let's hit for the derivative. So right here we're on step 4. We're ready to find the instantaneous rate. And here are those steps. And we were asked to solve for the instantaneous rate at time 5,000 seconds and 8,000 seconds. All right, so we have two answers. So let's hit Calc, which is second function trace. The derivative is choice 6. You'll see the graph appear. Give it time to think. And now I'm going to enter my first instantaneous rate of 5,000. And there's my answer. Ignore the negative because those are reactants and they're disappearing, but rates are always positive. 1.219 times 10 to the negative 6 molarity per second. And for the second calculation, 8,000 seconds, second function trace, take the derivative, choice 6, and now I'll type in 8,000 seconds, and there's my next answer. 6.543 times 10 to the negative 7th molarity per second. We have found the instantaneous rate at two different time intervals. Given the same list, we're able to calculate average rates by taking two concentration change over the change in time, or we can find a derivative of a curve and calculate an instantaneous rate. Let's go on and check your number 16 together. The rate of disappearance of HCl was measured for the following reaction. As time goes by in minutes, the concentration of HCl is decreasing. HCl is a reactant, so it's getting used as time goes by. Let's fill in the following grid and see what happens. So I'm going to clear out the screen. First thing I can do is just kind of change over the time from minutes to seconds. So 54 times 60 would give me 3240 seconds. 107 times 60 converts that into seconds. 215 times 60. And 430 times 60. So that was an easy column to fill out. So we have time both available in minutes and now in seconds. We have the concentration of HCl, and we want to go and calculate average rate in molarity per second. So calculating average rate for the time interval between each measurement. So remember, there is no interval at time 0. We begin here comparing line 2 with line 1. 1.58 subtract 1.85 divided by the time interval, and it wants it in molarity per second. So I'm going to take the time here in a second, not the minutes, but the seconds, so I get the unit they asked me for. So that time interval was 3240 minus 0. And here's the rate given to us in molarity per second for that next line, 8.33 times 10 to the negative 5th. How about the next? We'll hit 1.36 minus 1.58 over the time interval of 6420 from 3240. And now I have a rate 6.918 times 10 to the negative 5th. 1.02 from 1.36 divided by the interval of 12,900 and 6420. And now I have an interval here of 5.25 times 10 to the negative 5th. And one more, we'll fill this out, the last line, 0.58 minus 1.02 over the time interval, 25,800 and 12,900. And now the rate is given to me as 3.41 times 10 to the negative 5th, all molar per second units. So calculating average rates, just to remind ourselves, we're taking the change in concentration of our reactant, which was HCl, over the change in a time interval. And we just do that on our calculator. There's no need to show that, even on test day. Now it asks us to determine an instantaneous rate. So see what we're doing? We're practicing an average and an instantaneous. The instantaneous rate, I really encourage you to just practice the steps so you get fluid with, I know it's a long step, but you get faster and faster each time you do it. So we're going to be asked to calculate both in molarity per minute and molarity per second. So we'll have two different lists we're going to generate. So let's go back into our lists, clean them out. There we go. And I'm going to type in time in minutes first. So 0, 54, 107, 215, 430. I'll go in and type in the concentration into list 2 next. 1.85, 1.58, 1.36, 1.02, and 0.58. Alrighty. So I've got these two lists, list 1, list 2, and I'm doing that because I'm going to solve first for minutes. Alrighty. So now we want to calculate choice 0, way at the bottom, exponential regression. I want to do that for list 1, comma, list 2, and I get an equation. I have to transfer that to y equals. So I hit y equals, clear out what's there from the last problem. Let's transfer it over, and here's those steps. VARs, step 5 down here, statistics, the equation, enter. And it carries that right over for you. Check your window. This time I'm going from 0 to 430, so I'm going to just minimize that a little bit. I'm going to put 500. That'll be plenty big for what I'm doing here. And the concentration is going from probably like 0.5 to 1. So I'm going to make my Y max. Looks like if I make it a 2, I've got plenty of room there. Alrighty, so always check your window so you don't get a domain error. Now we've got our Y equal in there. Let's hit second function trace is the calc. We want the derivative, choice 6. And you'll see a graph. Give it a moment to think. And the derivative for time 75 comes out to be 0.00401. And that's a molarity per minute. And now let's do 250 as well while we're here. So second function, oops, that's wrong. We want choice 6, and this time we want for 250 minutes. And here I come up with 0.0025096, and that's molarity per minute. But we have one more step to do. That's molarity per second, and here's what I think the easiest thing to do. If we go back to our lists, I'm going to put my cursor right up here on list 1. I'm going to change those minutes into seconds by simply saying list 1 times 60, enter. And now I've got all those entered in as we had calculated, and I don't have to retype them, so I just make the calculator do that. Alrighty? But we have a new equation we have to solve for. Alrighty, so back to stat, calc, choice 0. We're going to find the exponential regression of list 1 comma list 2. And there's our equation. Transfer it over. We got to get that into the y equal so we can graph it. Y equal. Clear out what's there. Vars, choice 5, statistics. Scroll over to the equation. Hit enter. It brought it over for us. How are our windows? Not big enough, so 0 is good for the minimum, but now look, I've got seconds going to 25,800. Maybe I'll just do 27,000, and that ought to be pretty big, so that will work. And the concentrations will still work from 0 to 2, so that's fine. Alrighty, checking the windows so we don't get a domain error. Second function, calc. We want to find the derivative. And at 75 minutes, oh, I didn't have that exact, 75 minutes. So, all right, we have 75 times 60 to turn my minutes into seconds. And now I have 6.691 times 10 to the negative 5th molarity per second. Maybe I'll do this part first. I'll do here 250 times 60 to change my minutes into seconds. And I get my next I think I messed that up. Let me hit that over. So my y equal is in there. I want to calculate a derivative. And this time when I hit, I want it to be for 250 minutes, but in a second, so I multiply that value by 60. There it is. Now I got it. I did it twice, sorry. 4.183 times 10 to the negative 5th molarity per second. So again, 3 practices so far of calculating instantaneous rates. Very good work in making sure that the key sequence becomes familiar and fluid. 17 talks about rate expressions, and this goes back to the previous page where we talked about knowing the stoichiometry of a reaction helps us to write a rate expression. Here we have an equation where peroxide is decomposing into H2 and O2, and this equation is balanced as is. So as the change in concentration of hydrogen peroxide over its change in time is directly equal to the change in concentration of the appearance of hydrogen over its change in time is directly equal to the appearance of oxygen over its change in time. The rate expression, all coefficients of 1, so they are all equivalent values. Here we have an equation with some stoichiometry involved, 2 to 2 to 1. Here's where we place the fraction, 1/2 the change of concentration of our reactant N2O over a time interval, delta T, is directly equal to positive 1/2 the appearance of the product nitrogen over the change in time, which is equal to 1/1, which I just drop out, the change in concentration of the product oxygen over a delta T time interval. And one more we can write together. The disappearance of nitrogen, this 1 over 1 is just telling us it's a coefficient, not mandatory. Sometimes I find myself doing it out of habit. Is equal to the disappearance of hydrogen over a time interval. And what's appearing is the concentration of ammonia. So the stoichiometry gives us these equivalent values. For every 1 nitrogen, only 1/3 of hydrogen is consumed, and only 1/2 of its value of ammonia would appear. These are called rate expressions. The next question has us consider rate expressions again. Considering the combustion of hydrogen gas, let's check your number 19. If the rate expression for this reaction looks as follows: negative 1/2 the change in hydrogen concentration over a time interval is directly equal to 1 over 1, or drop that out, oxygen over a time interval, which is directly equal to the appearance, whoops, this needs to be negative, it's disappearing, positive 1/2 the change in concentration of water over the change in time. So here is the rate expression for this equation. Suppose hydrogen is burning at a rate of 0.85 moles per second. What is the rate of consumption of oxygen? So we're just comparing these two values, this expression right here. What this value is, this 0.85, is this expression that we just wrote there. Those are equivalent values. So the 0.85 is telling us the rate at which the hydrogen is being consumed. Negative 1/2, and I'm going to plunk in this value of 0.85 mole per second. That's the rate at which hydrogen is disappearing, is equal to 1 over 1, the rate of oxygen disappearing as well. And that 1 over 1 I can just drop out. So the change in oxygen over the change in time, negative because it's a reactant, so it's being consumed. And so this is what we're being asked to solve for, just that expression, 1/2 of 0.85. Did you get 0.425 like I did? So the change in concentration, its rate, that's what this is 0.425 moles per second. What's the rate of formation of water? Well, here's what we know. The rate of the consumption of hydrogen, 0.85, representing this value right here. But now we want to compare it over here to the value of water. And so water, its stoichiometric ratio is equivalent. Notice a 2-to-2 ratio. So now positive 1/2 the change in concentration of water over its time interval. And this is what we're solving for. It will be a number, and you can see to make both sides equal, it's going to be the same value. 1/2 of 0.85 times 2 is 0.85. That's the concentration change of water over its time interval. Alrighty? So think about the same amount of hydrogen that's consumed represents the same amount of hydrogen that appears. It's a 2-to-2 ratio, same number. But only, hydrogen gets consumed at 1/2 the rate of oxygen. Alrighty. And let's take a peek. You have one last part to check with me to make sure you have an A+ on this assignment. Here we have a reaction that was carried out. 2 NOs plus Cl2 make 2 NOCls. Carried out in a closed vessel. If the partial pressure of NO is decreasing at 23 torrs per minute, what is the rate change of the total pressure in the vessel? Let's start by thinking about the stoichiometry. So 1/2, and it's disappearing. The change in partial pressure of NO over a time interval is equal to negative 1 over 1, the change in partial pressure of Cl2 over the change in time, which is equal to positive 1/2 the change in concentration, that's a delta, sorry, change in the partial pressure of NOCl over a time interval. So what have they told us? They've told us partial pressure instead of molarity units, but the math is still the same. This value, the partial pressure of NO, 23 torrs per minute. And so if I want to know what's happening with this particular reactant, that 1 over 1 I'll just drop out, its change in partial pressure, decreasing as well, would be 1/2 of 23. 1/2 of 23 is 11.5. So partial pressure of Cl2 is decreasing at a rate of 11.5 torrs per minute. Whoops, I'm sorry, I'm off the page. And now let's compare these. The rate of appearance of NOCl really is the same value because the fractions are the same in front of it. So the disappearance of your reactant at 23 torrs per minute is said equal to the same value, positive 1/2 the change in partial pressure of NOCl over its time interval. What makes these two equivalent is the same number right here, number 23. So the partial pressure of NOCl is increasing because it indeed is a product at a rate of 23 torr per minute. And that is an A+ on your homework assignment. Good work.